Before we start, do you have any questions for me? No questions? All right. All right. So let me just do a brief recap of what we are doing so far. So far, what we have learned is we've learned the basics of deep learning. We started with the introduction of deep learning, and we talked about use cases, and afterwards, we all right. So afterwards, we started with learning TensorFlow, and we understood the power of lazy computing. And then basically here we learned basic constructs that were used throughout the course. And afterwards, we talked about the basics of neural networks, whereby we learned that we can actually the neuron is nothing but a neuron as such is nothing but multiple inputs multiplied with weights, and the summation of that, and the overall summation then passed through something like a step function that we call an activation function. All right, so that was the perceptron model, and then the same model, um, essentially when you stack many of such units together, that becomes the multi-layer perceptron model. All right, so this is where we started, and then we learned how to find out the various weights by using the gradient descent and using the backpropagation. So that's what we learned in the third session, and afterwards we learned in detail about training deep neural networks, whereby we we talked about multiple various problems. We talked about optimizers. We we understood what were the various optimizers and so on. So, and afterwards we started with the convolutional network. So as part of this, the uh, most important part was while so far during the training of deep neural network, we understood that if we have multiple layers of neurons, the input going from here to all of these weights multiplied to them and so on, and so on and so forth. So we generally get really good answers. We generally get really good answers, and we got around 93% accuracy with MNIST having just 2 hidden layers. All right, and then and then in the last session on CNN, we understood that we could make the performance really good for the solutions around image processing using CNN. All right. So what was so great about CNN? That instead of representing the neural network as a single line of neurons, a one-dimensional, here we represented the neurons as a layer, as a two-dimensional layer. And later on, we also discussed that how our our input layer or any layer has 3 dimensions. All right. So So that was an so that's what we discussed last time. And so what we understood was that, let's say this is how we connect our layers. So we move a rectangle around on the input layer to project on the next layer, and so on. And we keep on doing that again and again. The bigger the strides are, the smaller will be the output. Strides as in how many jumps are you making while moving this rectangle on the layer. So that's what we discussed in the last session. Let's just quickly go over it and then continue from there. All right. Uh, there are yeah, there's some questions. One is, will you cover unsupervised learning? So unsupervised learning, we'll just give you a quick overview that which algorithm is used in what circumstance. All right. And there are some parts of unsupervised learning we learned already as part of the previous session, but here the things that we are going to discuss further is uh, there are we are going to in the next sessions we're going to learn about the reinforcement learning and the recurrent neural networks, and and uh, and we'll also plan to give a brief overview of NLP and unsupervised learning. All right, we'll just plan a brief overview of various techniques. All right, a question from James will we be going an extra week over to finish cover everything, or are we on track to finish the week? So we should be we would need one more week probably after this. All right, we would need one more week after this. All right, a question from Pavan is NLP introduction. Yes, we'll do that. A question from Bintao is, more projects needed to be written in my resume. That's right. That's right. So we are going to introduce some more object detection questions and problems with respect to this, like CIFAR. That's another project that we're planning to put other than MNIST, that object detection one. And then we can utilize these smaller projects in a larger projects. All right, and we'll see what all we can include, because in the RNN, after we do RNN, then there are many other things that we could experiment with. All right, so after the RNN, we will again revisit what all projects we can include and what all additions we can do as based on the next discussion. All right, so all right, great. So last time what we learned was that in that as part of the research, people found that if you have two-dimensional layers and you operate on two-dimensional layers, the general outcome is far better. So the the it was based on the biological findings, where it was found that the, visual cortex also functions in the same way. All right, so all we do is, all right, so essentially the input layer, the image, we took an example of image, and mostly the CNNs are used for object detections, basically the image processing, as well as CNNs are also used in video and similar use cases where two-dimensional Cartesian coordinate system matters more. All right. All right. So all right. So this is what we discussed earlier. So all we do is we take a rectangle, okay, and we move that around the layer, and how much we move and should we leave the padding or not, that those are basically the hyperparameters. and and how much we move is called stride. Okay, so this animation generally shows that how is the next layer being generated from the previous layer. Okay, the translation that is involved, generally we multiplied various weights to individual pixel and then sum that up, or some other technique that we could use to that would result in the next layer. Then we learned about how the weights are applied and what kind of weights are applied. So we talked about filters. So essentially, let's say we have a filter like this, where this filter is going to get multiplied to various sections and the results are getting generated. So we continue like this till the last and so on. So, all right. Now, then we talked about within our layers could be three-dimensional, right? Our layers could be three-dimensional. Let's say we have an image has x and y coordinate that we all know. An individual pixel, if it's a black and white image, individual pixel will have an intensity, right? But if the image is colored, then we will have we will have three layers. That's our z direction. That's the third dimension. And the channels basically here represent the third dimension: red, green, and blue, because in every dimension, what is the intensity that would decide the overall color at every point in the image. Then when we apply multiple filters, each filter results in one layer, right? Each filter results in one layer. This layer is a resultant of the filter being multiplied, being applied, this filter being applied on all of the layers in the previous all of the sublayers of the previous layer. Okay, so this map 1 would be applied to the whole cube, and map 2 will be applied to the whole cube, and so on. And this cube actually moves like this. Okay. Question from Bintao is, does channel consist of three colors and with 3D? Yes. Channel, the third dimension in the image is the colors. All right. So the number of maps, the number of filters that we apply on the image, the number of filters that we apply on the image would be the z direction of the next layer. Okay, so if we have 20 filters applied on this one, we will have 20 layers, and so on. So this is the way we generally use the. So this is the way we basically use the CNNs to generate the outcome. All right. So this rectangle that we talked about, this rectangle is called recipe fields, and these are either called the sublayers, or we also, right. So these are also called sublayers when we have this slice, and right. So we'll talk about these things. then so this is what we talked about, that to generate a neuron in the next layer at ij column, ijn for the kth feature map. These are the this is how we determine which pixel to use in from the previous layer. So I think this diagram will be is more clear. So for, let's say, this pixel Zij in the output of the neuron located at I and j, and for the feature map k. All right. So right. So this, the value of z is a function of the value of z ijk is a function of previous layer, and we also talked about, I think this we have already talked about, so we can skip quickly. So um, how much is so based on the width of the receptive field and the strides and based on that we can generate the next layer. I think the reason why we are talking about this one is this formula. Okay, so the value at this point I, j, and k is equal to a bias, a, a, a biased variable. This bias is essentially same for the whole layer. Okay, same for the whole layer. That's what it represents, and plus summation of all of the summation of the multiplication of all of the points, all of the pixels in the previous layer with the weights. The weights are common for the whole feature vector. So the same weights are applied over and over to this. So weights are basically this bigger matrix. Okay. Weights are essentially this bigger matrix. So that's what happens when we are doing the computation for the next layer. Okay. A question from Binta is that does convolutional layer consist of maps which are constructed by the filters? Does convolutional layer consist of maps which are constructed by the filters? So yeah, so feature maps or filters, we are saying the same thing. So how should I say? So let me just explain to you. All right. So let me explain. So basically, when we are applying a filter, or we are applying a filter, we generate this sublayer. The sublayer is also called the feature maps. All right. The sublayer is also called the feature maps. Yes, so you're right in that. So essentially, when we are applying the filters, we are getting the sublayers, and those are called the feature maps. Now, moving ahead. So basically, what's happening here is we are taking the weights. This, you can say, when we are applying our filter, say this is our filter. So if we are applying that filter, those are called the weights, and those weights are being applied on every rectangle on each layer, and we're getting the summation of that one as a single value. So, and as we move that receptive field, we get more and more points for the next layer. All right. So I hope this diagram is clear, right? So this is the one that we talked about last time. All right. This is how the next layer is generated. The Filter is also called kernel. The filter is also called kernel, and we are applying this kernel is a composite kernel, which it has uh, basically three different kernels for each color. This one is for say red color, this one is for green, this one is for blue. So, and this kernel is being applied. All right. So the weights of the individual weights that you see here, -1, 0, and so on, these are these these values are what we learn via the backpropagation. These values are what we learn from backpropagation. This is the input layer, and we are applying the weights that we have learned, and we are generating the next layer. So essentially, the training CNN is all about finding these weights such that the output is matching with the desired output. All right. So then we talked about how to implement it. So in TensorFlow, each input image is typically represented as a 3D tensor, like height, width, and channels. Now, since there could be multiple such images, so the input will be basically a 4-dimension vector. The fourth dimension will be how many images are there in each batch. All right. And the weights of the convolution layer are represented as 4D tensor as the height of the height of uh, the receptive field, and width of the receptive field, and number of so yeah. So let's just explain you through the example. Fn is number of layers in the previous one, the z dimension, and then Fn dash is the number of so F yeah Fn dash is the number of layers in the previous one, and Fn is the number of such filters that are being applied. So this is number of filters. This is number of layers in the previous input layer. Okay, so these are the 4 dimensions. So the weights, the overall weights, are represented in this manner. Okay, so for each layer in the previous input layer and for each of the output layers, we have these heights and weights. Okay, that's what it means by weights. And then we have a bias term. This bias term has only one dimension, as in if that it is basically these are basically an array of values, one for each of the output layer. If you have 20 output layers, there'll be 20 bias terms. That's all. Okay. So all right. So where exactly were we? All right. Never mind. So we'll just continue from here. Actually, we had talked about all of this part. Okay, so I'll just go this quickly. Then we try to create our simple example. Here x equals to tf dot placeholder. This is what? This is basically the input that will feed later. And then we defined a convolutional layer. Let me go back here. So we loaded the image. So we loaded the image and using the from the MNIST, and then we defined the batch size, and afterwards we created these filter sets. Afterwards we created first the filters that we created were filled with zeros. Then we put one filter from our side, the vertical line and horizontal line, and then we applied that filter. All right. So then we did an example using say TensorFlow. So here we are creating this input layer. This input layer has a shape of, this is like total number of batches, height and width and the colors. Okay, so this is basically the shape of X. And the next is the convolution layer. The convolution layer is created using conv2D. We are feeding the X, the input layer. We are feeding the filters that we have just created. Then we have specifying the strides, and then we are specifying the padding. All right, we'll talk about this type of padding. So once we do that, then we run it, and then after running, we get the output. All right. So here the stride is a 4-element 1D array. Okay. So where the two central elements are the vertical and horizontal stride, as in while moving the receptive field around the while moving the receptive field on the input layer, how many steps, how many jumps should we take? Or if as h and sw is 1, that means we are just going to slide the receptive field one at a time. Okay, so here in the as of now, as of now, the first and last element should be 1 in this strides. Okay, and right now we can only apply the we can only move in the z direction one at a time. All right, so right now the TensorFlow does not support moving in z direction more than 1. And okay, the padding part here, the padding part is whether same or keep it different, uh, is basically another hyperparameter. Okay, so if we say valid, that means the convolution layer does not use the zero padding and may ignore some of the rows and columns at the bottom and the right of the input image. So when we say valid, the rectangle that we are going to move on the input layer, in case it goes beyond the boundaries of the image, it doesn't go beyond the boundaries of the input image. That's what it means by valid. If set to same, then the convolution layer uses the zero padding if necessary. If the when moving, if it has to go beyond the edge, right? It has to go beyond the edge, then it's completely okay, and it puts the zeros in instead of just ignoring those parts. All right, since while moving the input receptive fields, if we, let's say we have a stride such that if we don't move, we might miss some of the input data. In that case, if we don't want to miss some of the data, we can use the same as the padding. All right, so like for example, in this case, if we have the first was this and our stride was of 1 2 3 4 5, and we move to the next one by 5. Okay, now we completed this. Now the next one would be this one, but since that is going the beyond the actual data, if the padding is valid, then these two will never be covered. Okay, is this clear to everyone? All right. So a question from Binta is, the first and last elements of the strides must be currently equal to 1. The first and last represent how many? So this first actually represents, this one represents the Okay, so this basically represents how many jumps to make in the z direction. Okay, this one represents that, and this one I think represents the strides to make on the output part. All right, so both of them as of now should be one. Okay, and I think this one of this so one of this actually represents how many instances to skip, and how many layers to skip in this. Okay, so which we want to keep it one, and as of now the TensorFlow only supports one, so only these parts are what we can specify. Okay, all right, so if padding is valid, then these pixels in the input layer will get ignored. All right, if padding is same, okay, let's say we are right, we're starting from here. So in this case, the number of output neurons is equal to the number of input neuron divided by the stride, rounded up. Okay, so basically here it does not miss it does not miss it does not miss any of the pixels. Okay, and and hence the, the and hence the total number of steps it takes are basically multiples of the stride size. Okay, so that's called, because whenever it is going out, it just fills it with zeros. All right, so as you can see that there are quite a few hyperparameters, meaning we can choose number of filters, right, their height and width, their strides, and the padding type, and also the various ways we can connect the layers that anyway is an open question with the whole neural network. Okay, so as always, you can use the cross validation to find the right parameters, but this is very time consuming. Okay, so the the other problem with CNN is the memory requirements, that it requires a huge amount of memory, because the reverse pass of the backpropagation requires all of the intermediate values compared during the forward pass. So while we are training, at that point of time, we require all of the layers, and therefore the training requires more memory as compared to applying the network, applying the CNN. Okay, so consider a convolution layer with 5 by 5 filter, and so imagine that we have a CNN with 5 by 5 filters outputting 200 feature maps, okay, of size 150 by 100 with a stride of 1 and same padding. Okay, if the input is 100 by 100 RGB image, meaning 150 by 100 by 3, that is the input size, then the number of parameters will be, anybody? Yes. All right, so Let me explain. So what does it mean? So since we have, right? So let's go back here. So what we have here is, what we are saying that this is our input image size, right? And the filters are of size 5 by 5. So 5 by 5 into 3, right? So the filter size is 5 by 5 into 3, one for each color. Then there is a bias for each of such filters, correct? Multiplied by 200, since there are 200 feature maps, or you can say 200 such filters being applied. So the total number of weights are 5 into 5 into 3 into 200, right? So Pratik, you're missing 1 3, okay? And hence the total number of weights that we need to keep in the memory will be this much per layer. Okay, if we have more such layers, there will, let's say we have 3 consecutive layers of such kind, so there will be it'll be multiplied by 3. Okay, though it is far less compared to the fully connected layers, but still it is huge. Okay, so each of the 200 feature map contains 150 by 100 neurons, and for each of the neurons need to compute the weighted sum of these many inputs, that is 225 million float multiplications. Okay, so while we are doing the computation, you can see that each of the neurons need to compute a weighted sum of its 75 inputs, right? Because the filter size is 5 by 5 and on 3 layers. So that every time for every output neuron, we need to do 75 computations. Okay, need to do 75 computations, and hence 150 into 100 into 75. Okay, so those many float multiplications. All right. So you can see that in case of the computation in neural network, there are just too many computations, and that's why we generally prefer GPU. But GPU has less memory, and the best GPU you can buy even today at a very high cost is around 16 GB RAM GPU, right? So if the feature maps are represented by 32-bit float, then the CNN layer output will occupy 200 by 150 into 100 into 32, right? So this much memory, which is about 11.4 MB RAM, and that's just for each one instance. If training batch contains 100 such instances, that is equal to 1 GB of RAM. All right. So when making a prediction for new instance, the RAM occupied by one layer. So while we are doing the inference, as in when we are applying our neural network and getting the results. So while we making the predictions, we could just drop the one layer's computation once we are one layer's data or one layer's numbers as soon as we are done. So we can just drop that whole layer, right? But in case of training, we can't really drop a layer, right, from the memory, because it will be required during the backpropagation. Okay, so because so the amount of memory that is needed is less. Okay, so the amount of memory that is needed is less in case of predictions, while training we require bigger memory. Therefore, predictions can be done on very thin devices such as mobile or thin as in the devices, low-end devices. The predictions could be done on low-end devices, while training is generally done on high-end devices. Okay, so high-end devices because the training requires more memory and the predictions do not. All right, then we also discussed about pooling layer. The goal of pooling layer is to basically shrink the input image in order to reduce the computational load, the memory usage, and number of parameters. Okay, so the pooling layer is very much like you can say like we are taking an input layer and converting those pixels into just one single pixel. That's all. So it reduces the input image, makes the neural network tolerate a little bit of image shift. This is called location variance. So when we are taking an average of say set of pixels, we're basically averaging out various values, and hence the pooling also helps us in overcoming the minor variance here and there. All right. So just like convolution layer, each neuron in the pooling layer is connected to the output of a limited number of neurons in the previous layer. So each neuron in the output is the output of just give me a second. All right. So So basically, the calculation in case of pooling layer is exactly like the usual layers, just that just that we 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 generally have a bigger strides, right? We generally have bigger strides. So pooling layers don't have any kind of weights. We are not this when we are aggregating the receptive fields, we are not applying any weights. It's just a static function that does not learn. Okay, it could be max, mean, or some other form. Okay, so that's called pooling layer. So here, the below figure shows a max pooling layer in which which is basically the most common pooling types. We have 2 by 2 pooling kernel. It's a stride of 2 and there is no padding. Okay, so meaning we are if there is a stride of 2, what will happen is the image will reduce to 1/4 size. All right, if what does it mean by stride by 2? Stride by 2 means this rectangle will jump by 2 every time, and when that happens, that essentially means that that essentially means we so let's say there is a rectangle here, we're moving by 2. That means if there are 4 possible pixels in the input, it'll move only twice. Okay, so the size of the input image will reduce by 1/4. Width will reduce by half, and height will also reduce by half, reduce to half, and hence the overall image will have 1/4 area. Okay, so not only does the max input value, okay, so note that so I actually read it wrong. So the only max input value in each kernel makes it to the next layer, and other inputs are being skipped in this particular max pooling layer. Okay, so there could be many kind of pooling layers, such as max or average. Okay, so pooling layers are very destructive layers. as even with 2 by 2 kernel and a stride of 2, the output will be 2 times smaller in both directions. So the area will be 4 times smaller, that is 25%, and hence we are dropping around 75% of the input values, right? So each time our 2 by 2 filter is applied, each time our 2 by 2 filter is applied, we are only keeping one value out of 4. Okay, so a pooling layer typically works on every input channel independently. So the output depth is the same as the input depth. We may also pool over the depth dimensions, in which case the image's spatial dimensions like height and width remain unchanged. Okay, but the number of channels is reduced. Okay, so sometimes we may also pool the multiple input layers into one. Say, for example, if you want to just convert a colored image into a black and white, we can just pool over the third dimension, which is color, and that way we could reduce the input channels. Okay, so let's implement the max pooling layer in TensorFlow using 2 by 2 kernel with a stride of 2. Okay, so we are taking a small rectangle of 2 by 2 and we are moving it every time by 2, and then we are doing the max of all the pixels. That's all. No padding, and then apply to all the images in the dataset. Okay, so you can see here, first we have defined the input x as placeholder, and the max pool equals tf.nn.maxpool, and there we are saying this is the input, this is the case size. Case size means the kernel shape, right? And since we are only right, so right now it basically only applies a particular kernel at one instance. Okay, and also it does not a very important point is that when we are applying the pooling, then it does not support pooling over both spatial as well as the depth dimension. So either x and y or z. We can we can only pool the multiple layers, right? Either we could move in z direction, or we can pool in z direction, or we can pool in xy direction. So the either this value as well as this value, both of these values must be equal to 1, or the third value should be 1, the fourth value. Okay, so this means the first one means how many instances do we do of how many instances we consume in a single shot while doing the max pooling or average pooling. How many layers, how many instances do we pool together? Second one is Second one is what is the window size on x direction and y direction. Third one is y direction. And fourth one is Z, which is the channels input, the input layers. Okay. So far, either both of these should be one and this should be something else, or this should be one and they could be something else. All right. So So while defining our rectangle that is applied over the input, we could define it in the 4 dimensions, that the way we define the filters, right? So in the similar way, we could define the kernel. We could define the kernel in these 4 dimensions: batch size, height, width, channels. All right. So exactly the way we did it case of normal layers, the convolution layer. So the CNNs are generally composed of, the larger CNNs are generally composed of a CNN layer followed by a pooling layer and the repetition of those. Okay, so if you want to do average pool instead of max pool here, you could just say avg underscore pool and so on. All right, the rest of the things are same. There's strides, padding, and so on. And here we could just run the pool as usual. Okay. A question from Binta. A question from Binta is, could you draw a graph to explain K size and its parameter? Okay, sure. Let me just draw. Okay. So imagine that we have our input layer. Okay. So imagine that we have our input layer, something like, say, right? Okay, so imagine that this is our input layer, and let's say this is the, say, number of channels that we're defining here. How do you move it? Okay, so let me just try moving it. Okay, never mind. So this is, let's say, this is our input layer, which it has some pixels on the input side. These are the pixels, and these are the channels, right? So there could be 3 channels generally. This is the red, this is green, this is blue. Okay, so when or actually the max pooling is applied over the results of the previous convolution, so there could be many such layers. Okay, so the K size, as we talked about, the K size is this, right? The size of the receptive field. Now there's a fourth dimension, that is, many such images would be coming. There is one this image, the next image would come. So the K size, the first dimension in the filter is one, meaning that the filter must be applied per instance. Okay, we can't have filter which is different for different input instances. Okay, so the fourth dimension I can definitely not visualize here. Okay, so the first one that you see is the dimension where it says that does the kernel vary per does the kernel vary per batch. Therefore, we are saying that the first value is always 1. Okay, first value is always having one dimension, that is same for all of the kernels. All right. Now, the second and third, okay, so I'll just uh, say this is the K size 1. The 0 was for batches, right? So 0 was for batches. Let me just say per instance. Okay, and that was the case size 0. Okay, so case size 0 was per instance. All right, now then this is case size 1. Okay, and this is case size, this is case size 2. Okay, so you can, all right, so this is 2, this is 1. All right, and the case size, that is basically the kernel that's going to be applied on which directions, that is, this is the um, size of kernel, how many layers will it cut across. Okay, that's the Z. So this one is Z. Okay, if you think about it. So generally, either the case size, this could be okay. So right now it does not support cubical k kernel size, right? Let me go back here. So either it could be of this shape, like only horizontal, or it could be only vertical. It could be only vertical like this. Okay. It could be only vertical. Uh, Let me just try trying again. So the case size 2, case size not 1 here, it has to be 3. Okay. So this is how you can visualize. So when we are going to definitely move it. We are going to move it further to another location. So that's basically the kernel size. So kernel size, either it could be only like without the Z width could be 1, or it could be only in this direction like this. Okay, the either this could be 1. Okay, either this size could be 1, or both x and y are 1 in this case. Okay, both x and y are 1 in this case. Okay, both x and y, okay, both x and y are 1. So when you are applying the max pooling, the kernel could be like this or like this. Okay, here this is supposed to be the kernel size 1 like this. Okay, I just wanted to demonstrate. So the third dimension is non-zero and non-1 in this case. So actually, it is going to be something like this. All right. So 1 pixel from X, 1 pixel from Y, and multiple pixels from Z. Okay. So this is the kind of thing it is. All right. So so either the Z dimension is 1, or both X and Y are 1. All right. A question from Inta is, what's the difference between case size and filter on their parameters? Yes. So case size and filters. So filters are used in case of convolution layer, and pooling layer only has a so okay, let me put it again. So usually in case of convolution layer, the filter that we are using are basically trainable parameters. So it has the weights which are trainable, right? Here, in case of pooling layer, we we hard code this part that we want to either do max, min, or and so on. Okay, so in that way, here we are defining the case size in the same way we had defined our filters earlier. We have defined the filters and their dimensions, and we fed the filters earlier. In case of convolution layer, we feed the filters here and let it train those filters. Let it basically figure out the weights based using the backprop. Okay, and here we are basically telling the we are basically telling that this is the size of the kernel and just find the max of it. Okay. So that's the difference between convolution and pooling layer. In convolution, we're training the kernel. We're basically figuring out those weights of the kernel which will give us desired output. And here we're just finding the max or average or some other form. All right, great set of questions. Moving ahead. Now, here's a very important part. So whatever we have learned so far, we learned about fully connected neural networks, we learned about CNNs, and we learned in CNN, we learned about convolution layer and pooling layer, right? Now, when you are trying to solve problem and you want to improve accuracy, you could utilize all of this knowledge. Most of it is intuition and most of it is hyperparameter optimization. Okay, so because of trying to solve or compete on a challenges, right? So because of trying to solve large scale problems, many researchers came up with many different architectures. So we're going to give you an overview of various architectures, and some of it you can take a look at in your own time. All right. So typically, CNN architectures stack a few convolution layers, each one generally followed by ReLU layer, and then a pooling layer. Okay. Then few convolution layers plus ReLU, and then another pooling layer, and so on. So convolution pooling, that kind of a pairing we do, followed by fully connected layers. Okay, so the input keeps on getting smaller and smaller as it progresses through the network, but it also typically gets deeper and deeper, meaning more and more feature maps. Okay, so here there were only 3 dimensions. When we applied, say, five filters, we got five feature maps. Then we applied more feature maps, and so the dimension is reducing, right? And the number of feature maps are increasing. Okay. And once we are through it, then we generally put a fully connected network afterwards. At the top of the stack, a regular feed-forward neural network is added. Okay. So at the top of the stack, we generally add a feed-forward neural network, or we can say fully connected one. Okay, plus values, and the final layer outputs the predictions. Okay, the final layer is nothing but softmax layer that outputs the estimated class probabilities. Okay, a common mistake is to use convolution layer that are too large. Okay, that are too large. We can often get the same effect as a kernel. So we can often get the same effect as 9 by 9 kernel by stacking two 3 by 3 kernels on top of each other. Also, in this approach, we have lot less to compute. Okay, so if we are using huge kernels, right? So if we have huge kernels and we have, say, smaller strides, then the output is going to be bigger. We can generally achieve the same effect by by 3 by so the size of a kernel, say 9 by 9, which is how much 9 times bigger than 3 by 3 kernels. Instead of using that way, if we use 3 by 3 kernel, and we can just achieve the same thing in the twice amount of efforts than 9 times. Okay, so that's what we are trying to say here. So instead of using bigger instead of having bigger output layers, instead of having huge convolution layers, okay, and all right, let me put it this way. So instead of using a huge kernel, okay, instead of using a huge kernel, try to use smaller kernel, but multiple of such, okay, multiple of such kernels. Okay, so over the years, variants of this fundamental architecture have been developed, leading to amazing advances in this field. And a good measure of progress is to look at these computations and observe the error rate in the computations, as such as ILS VRC ImageNet challenge. That is basically the de facto challenge everywhere. It is part of now Kaggle from this year onwards. So earlier they used to host their own challenges separate, but now it's part of Kaggle. So in this computation, top 5 error rate for image classification fell from 26% to 3% in just 5 years. Okay, so the top 5 error rate is the number of test images for which the system's top 5 predictions did not include the correct answer. Okay, so system's top 5 predictions did not include the correct answer. That was top 5 error rate. Okay, in this challenge, the images are large, 256 pixels high, and there are 1,000 such classes, some of which are really subtle, like distinguishing 120 dog breeds. Okay, so basically the ImageNet, it's also called ImageNet ILSPRC ImageNet challenge. So in the ImageNet challenge, the images are large, like 256 pixels, and there are thousands of classes, and in the classes could vary only slightly, such as dog breeds. Okay, so we looking at the photo, let's say we have to distinguish the dog breed just looking at the photo, and those are the kind of challenges that that ImageNet hosts. Okay, so basically these computations of ImageNet has led to amazing architectures, and by the way of arranging the CNN layers, and by the way of coming up with further all kinds of pooling and filters, they have been amazing advancements. Okay, so let's look at some of the best CNN architectures. The most widely known CNN architecture was created by Yann LeCun in 1998. Who is Yann LeCun? He is the head of machine learning at Facebook as of now, and he was he I think he implemented the backpropagation long back. Okay, so I think he was probably the first or first ones to implement the backpropagation. All right, so it was created by Yann LeCun in 1998 and widely used for handwritten digit recognition. So for MNIST. So here is his architecture. So there is an input layer that is, of course, 32 by 32 size. Okay. Then there is a convolution layer for him. For some reason, MNIST, he got the data of 32 by 32. I was hoping it to be 28 by 28. So then there is a convolution layer, then average pooling, then convolution, then average pooling, then convolution, then two layers of fully connected. The final one is basically the output layer. It has a size of 10. Okay. All right. So okay. So this was it was called AliNet, probably from Lekun. It was the name was from Lekun, and a question from Bidda is, there are so many kinds of layers in the table. Layers as in layers, right? Okay, okay, good. So let me just go over the layers again. So the first one is input layer that we all know. It's the input images. Okay. And then we have convolution layer. Here, the activation function we are using is 10h, that the one that we have used, we've explained earlier. This is the activation function. Okay. And then we are using average pooling, the one that we just discussed. So all we are doing is we are taking a rectangle of 2 by 2, right? Okay. Let's say we are taking a rectangle of 2 by 2, and we are having we are taking a rectangle of 2 by 2, and we basically jumping it by 2. Therefore 28 by 28 is leading to 14 by 14. Okay, leading to 14 by 14. So width and height both are being reduced by 2, right? And and this is the rectangle. Here we are using 5 by 5, and since we are here, maybe we are basically dropping some of it, some of the pixels, right? So some of the pixels are being dropped at this point. The last 4 are being dropped because that's less than width and height. So that's why we have the size of 28 by 28. Next one is after the convolution, then we have average pooling. Yes, average pooling we have talked about. This after this combination, there is another similar combination. Okay, so after average pooling, again we are doing the 10h kind of translation from here to here. Again dropping the last 4 pixels. Again dropping the last 4 pixels. That's why 14 by 14 became 10 by 10. Okay. Again, activation function is again 10h. Then we have average pooling. Again, in the same way, we have 2 by 2 kernel size and the stride of 2. That means the width and height will reduce to half, right? Because we're jumping by 2, and therefore, right? So this is what we have, and okay, and here we are saying how many parallel feature maps do we have? And this 6, 6, and 16, and 16. Okay. Next, after average pooling, we have one more layer of convolution. This convolution layer is kernel size of 5 by 5, right? And the stride is 1. Okay. Now at this point, what's happening is the size that was left after this point is 5 by 5. And since there is only one stride, we are sorry, 1 by 1 kernel size, therefore in every dimension only one value is left, since we are not doing the padding here. Okay, this is the important part. So we are not using the padding, therefore 5 by 5 became 1 by 1. Okay, so here at this point of time, z dimension became of 120 size, while the x and y became 1 pixel each. Okay, so from here, where the z dimension was 1, as in there was no color, it was a grayscale. From here 1, it grew into 6, then 6, then 16, then 120 in the last. Okay, so this 120 is being used as 84. This is something, some translation is going on here. Okay, so these are 120 maps which being used at this point of time as the size of 84. Okay, yeah, that's correct. So what we could do is we could look at is that in here we have 84 neurons which are connected to these 120 neurons, and which are being further connected to 10 neurons. All right, so that's how it is. Is it clear now, Vidya? All right. Any other questions? All right, great. So I hope this is clear. So essentially, this is what's going on. This diagram that you see, there was input, then we have convolution layer, then pooling layer, then convolution, then pooling. And finally, there was one more convolution layer. That one converted this into one single dot and 84 dimensions. Okay. All right. All right. So I try to show this diagram there. Now, great. Moving ahead. So some more details about LinNet. So images are also 28 by 28 pixels, but they were zero padded to be, oh, these were the reason. All right. So they were zero padded to 32 by 32 pixels. So at this point, yeah. And normalize before feeding to the network. The rest of the network does not use any padding, as we discussed, which is why the size keeps shrinking as the image progresses through the network. So there are two reasons for size to shrink. One was we did not have padding. Second, we were having this second was because of the max pooling. One was whenever we were doing the convolution, so there was no padding, therefore those parts that did those parts were removed. And here, since stride is 2, therefore these are being converted into half. And next is, since here the size dropped from 14 by 14 to 10 by 10. Why? Because we did not have the we did not have the we did not use the padding. Therefore, after 10th, when it encountered 4 more pixels, it just dropped them because the filter size was 5 by 5. Okay, so that way, the because of filter size also, because of not using the padding, the the size of convolution layer also dropped. That's what we are trying to explain here. All right, now that was the first one, and okay, the next one was LXNet. LXNet was the one that won 2012 ImageNet competition. All right, so it was developed by Alex Krzyzewski, Ilya Sutskever, and Geoffrey Hinton. So it achieved 17% top 5 error rate. It is quite similar to LayNet, but much smaller and deeper, much larger and deeper, sorry. So LXNet was an extension of LayNet. It was much larger and deeper, and it was first CNN to stack convolution layers directly on top of each other instead of using pooling layer. All right. So instead of using convolution and pooling together, it basically stacked convolution layer on top of each other. All right. This is how it looks like. So we start with an input layer followed by convolution, then max pooling, convolution, max pooling. Then these 3 layers did not have any max pooling between them. Okay. Convolution, 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 and then finally fully connected one. So here it was based on the LeNet was based on MNIST. This one was for the ImageNet where we have to identify objects, and the size of the input was 224 by 224. Okay, and at this point, so the kernel size was here in the first layer. This is the kernel size. This is the stride, and the padding was same. Okay, and so on. So you can see that. All right, now this was a huge network, and you can see that even in the end, it has the total number two hidden layers, each of the size 4096. Okay. A question is, how can map size be smaller kernel size? Okay, how can map size be smaller than kernel size in LayNet 5? Okay, which one are we talking about? Okay, so map size 6, right here. Yeah, so map size is up to us. Um, how many such filters do we want to do in every dimension? That is up to us. Okay, we could have as many as we want. Okay, this we can have as many as we want. Okay, the way we can have any number of neurons in the hidden layer, in the same way we can have as many Z dimensions as we want. Let me go back here in the diagram. So here, if we just used filter with only one filter at this point of time, or only one kernel at this point of time, then there won't be any Z directions, right? So here we are saying that we are applying multiple filters. Each filter results in one layer, so we are applying multiple such filters, or multiply, or applying multiple such kernels. So if we say 120, then there'll be 120 dimensions here. Okay, that's what it is. All right, good question. Good question. So again, and at the C5, right? Yeah. A question is what happened at this point? So what happened at this point? So do you mean that how did 5 by 5 got converted into 1 by 1? Is that your question? So earlier the image was 32 by 32 that was padded with white space that got converted into a layer that has dimension 28 by 28, and the Z direction, there were sublayers, 6 sublayers. You can call that feature maps, and then the next layer in the sequence was 14 by 14, and the maps were 6, and then 10 by 10 and 16 were the maps, and so on. All right. So here at this point, do you mean to say that how did we convert 5 by 5 into 1 by 1? Is that your question? So the size of the input layer is 5 by 5. Okay. Yes. A good question. Question is, can a large kernel be used for a smaller map size? Okay. So here this map size is different. Here this map essentially is how, how many kernels do we want to use in every dimension? It is up to us. Okay. If we have 120, we want to apply 120, then we'll get 120. Okay. Now, next question is how can a kernel size of 5 by 5 lead to 1 by 1? Yes, of course it can. All right, of course it can. So imagine this. Imagine this. Okay, imagine that we have, let's say, instead of this smaller size window, we have a bigger window. Okay, so let's say our kernel is of this big size. Okay, our kernel is of this big size itself. Okay, all right. So let's say this is our kernel. So we will take it and apply here on the whole, right? So since we can't move, since there is no padding, so the whole layer will result in a single pixel. The whole layer will result in a single pixel. That's why this whole layer, so the whole layer size is equal to the kernel size. Therefore, there's only one pixel that is being generated out of the whole layer. But there are multiple such kernels. There are 120 such kernels that are being applied again and again on this layer, and hence there are 120 pixels that are being generated here. So the size of this layer is 1 by 1 into 120. All right. Was I able to answer your question? Okay, good. A question from Pratik is, will pooling layer always have the same number of maps as the input layer? Um, Actually, there is no hard and fast rules. So here it seems that the average pooling layer is having those many maps. So generally, since we do not apply, as we earlier read, that we are not pooling over the z direction. Generally, we only pool over the x and y. Therefore, total number of convolution layer remains as such, right? If we can actually pool over the z direction also, but we don't do that. It's there's no hard and fast rule, but we could always have average pooling here, the say kernel size 1 by 1, and say pooling over the z direction only. Then this will change. Okay. 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 A question from Ross is, how is the z, the kernel function, numbers are specified at each steps is not clear. Okay. Basically, that's what comes from the kernel. So when we are creating the kernel, if you take a look at this one, so this here, this last value, or let me just go back a bit to show you how does the, okay. So this dimensions of filters is what causes the total number of layers in the next one. Okay, here we have X and we are applying filters. So filter is what we have defined here. We are saying that it's the shape of our filter is 7 by 7 and the number of channels, and there are two of such filters. Okay, there are two of such filters. All right. So we can apply more and more such filters. We can create as many filters as you want, as we see here. And so we could just pass our filters to the convolution layer. Okay. So note that the filters is also a 4D tensor, X, Y, and how many and if it is varying for the different input channels, as well as how many ones do we want in the output. Okay, so that basically that is the, we can control that as per our wish. Okay, we can have as many kernels as we want. Okay, so yes, let me show you the, so number of filters could be as many as you wish. Okay, so here in the architecture, it doesn't, the way we can have any number of neurons in the fully connected layer, similarly we can have any number of Z layers in the output. Okay, based on if there are many such kernels. All right, good. Good set of question. Was able to answer Ross your question? Okay. A question is, I mean that to figure out the number of filters that were applied in one seems to depend on kernel size. Right. Actually, we have not explicitly defined it here. This is what is the parameter that is there. Okay. So it's basically something that we have specified explicitly. Okay. So we want these many 120 such kernels. So the dimension of these kernels is, the weights are 120 times this. Okay. So 120 times these many weights is what we have at this. That's correct, Pratik. Since MNIST since LINET was applied on MNIST, and hence the size, the z direction was 1, or you can say feature map was 1. Here we have explicitly said that we want to apply these weights with 6 depth. Okay, therefore we'll get 6 layers at this point. All right. So great. Moving ahead, so here in LXNet, we again have these many times we are applying these kernels. Okay. All right. So, okay. All right. So I hope this LXNet is also clear. So it has input, the pair of convolution and max pooling, then again the pair, then followed by 3 convolution, and then fully connected. Now, a question would be arising that how do we come to this? Okay, it's more of like creativity, or you can say arbitrary. Okay, or you can say that after too much of parameter tuning and hit and trial and experimentation, and sometimes we also call it somewhat intuition, right? So coming to a particular architecture is actually hard, and this is where a lot of research is going on. So we will basically cover the general architecture so far, and then we'll start with the RNN. Okay, great. So far we learned that by combining the convolution and pooling layer, we could do multiple things. And LXNet was one such example that applied apply the convolution and max pooling along with fully connected to give great results. Now, moving ahead, so to reduce overfittings, the authors of LXNet used two regularization techniques. First, they applied dropout with 50% dropout rate during the training to the outputs of the layer F8 and F9. So here they applied the regularization, okay? And second, they performed data augmentation by randomly shifting the training images by various offset, flipping them horizontally, and changing the lighting conditions. Okay. So, all right. A question from Vidya: is there a graph to match and explain LXNet? I'm not sure. I don't think there is a graph, but yeah, there is a pictorial representation of LXNet, which seems to match this one. That'll be on the next one. Okay, let me just help you this. So, okay, so I don't have a graph as such, but I can explain in case something is not clear. So there's an input layer, then have convolution with 96 feature maps, then max pooling with same feature maps and things like that, and so on. All right. So I don't think I have diagram for this one, but all right. All right. There'll be more advanced ones. Here we're just going with the basic ones. All right. In last couple of years, there have been drastic changes in the way we look at the CNN. All right. If something is not clear, I can explain or try to draw it. Okay. All right. So in LXNet, one regularize there was okay. So they used two ways to regularize the outcome. One, first they did the dropout. Second, did the data augmentation. Okay. So they did all kinds of changes to the image, which does not destroy the image, but that changes the entire image. Like, for example, flipping an image horizontally. Okay. So LXNet also used competitive normalization step. Okay. It's called competitive normalization step. Immediately after the ReLU step of layers C1 and C2, there was a normalization done, or called the local response normalization after C1 and C2. After C1 and S2, not C1 and S2. It is C1 and C3. Okay. So this, after this convolution layer, after applying a ReLU, as well as this point, at both the places, the competitive regularization was used. Competitive regularization means, sorry, the basically competitive normalization step, also called as local response normalization. Okay, so this form of normalization makes the neuron that most strongly activate inhibit neuron at the same location. So all it does is it picks up in every filter. All it does is, so in every how should I say, in every filter, what it does is it, for every value of pixel, it goes over the whole stretch and divides the individual's value by the square of all the values. Okay, so that's basically normalization at every step. Okay, so essentially comparison with the neighbors. Okay, comparison or competitive activation, that's what it does. So this encourages different feature maps to specialize, pushing them apart and forcing them to explore a wider range of features. So ultimately, it improves generalization. Okay, so this is what is done here at this position. So to compute the, so here we do, let's say these are the various values of which we want to do the local normalization. So what it did was it divided each pixel values by the sum of the total of all the pixels. Okay, so that's what it did. And k is just to avoid division by 0, and to the power beta is just to emphasize it a little bit more. Okay, beta is 1, then it'll behave like normal. We are doing the, we are computing the sum square summations and dividing the values. Okay, so in the previous layer, what is it doing is here. So immediately after convolution, it applied the response normalization. What it does is, it basically took all the values in the same, at the same filter level, and then did the square of each individual values, and then divided the individual pixel value by that squared value. Okay, so that's what it did. It's just like averaging out or doing the normalization, just that there are minor differences here. First minor difference was that the instead of summation alone, it was summation of squares. Generally, how do we find the average? How do we normalize? We basically, the way we normalize is we divide the individual value by the max, correct? By the max range, right? And here it was basically more aggressive. The individual's value was divided by the summation of squares. Okay, that's what it was done. All right. So summation of squares, and there are two extra parameters. One is k and beta. K is for avoiding division by 0, and beta is to emphasize furthermore and is a hyperparameter that we could control. Okay. If it is square root, let's say beta is 1 by 2, then this will be a square root of it, and so on. So howsoever we want it to be. Okay. So essentially, this was normalization step, dividing by the in each of the layers here at every position. We are basically doing the average of it. Okay. Now, so that was the LXNet, one of the differences from the standard at LXNet. So now there was another variant of LXNet called ZFNet, was developed by Matthew Zeeler and Rob Fergus. It won 2013 ImageNet Challenge. All it did was it actually used exactly like what LXNet did. The only difference was that it used different number of feature maps. It used different number of feature maps and used different kernel size and stride. So essentially, ZFNet was nothing but LXNet with different hyperparameters. Okay, so the ZFNet won 2013 ImageNet Challenge. Now the the one that won 2014 challenge was by Google, by a person named Christian Szegedi, and the name of the neural network was GoogleNet. So it sounds like a study of history rather than computing, but this is quite useful history, right? So it's like there was World War II, and then before this there was World War I, and then the Cold War happened. So this sounds like that. So GoogleNet is essentially kind of the World War II kind of thing. And here there was uh, basically just too many layers. So the great performance of GoogleNet came in the large part of the fact that network was much deeper than the previous CNNs, meaning just too many neurons. This was made possible by subnetworks called Inception Modules, okay, which allow GoogleNet to use parameters much more efficiently than previous architectures. GoogleNet actually has 10 times fewer parameters than LXNet, roughly 6 million instead of 60 million. Okay, so the core part of the GoogleNet is Inception. This Inception module is used again and again in GoogleNet. So basically, Inception module is a combination of convolution and max pool. Okay, convolution and max pool. So for the input is applied on these convolution network parallelly, and each of the, so you can think of this as one combo. This is one combo. This is one. This is another. And then we do the concatenation. All right. Then we do the concatenation. So essentially, this Inception module was the core of the GoogleNet. All right. So it's nothing but multiple convolution network in parallel and the series. Okay. So the notation here, when we are saying 3 by 3 plus 1, means that the layer uses 3 by 3 kernel with a stride of 1 and same padding. That means it's not the valid padding, it's the same padding. That means it's not going to lose the edges, right? So all of these have a stride of 1, okay? And there are some which are 5 by 5, there are some which are 1 by 1. Okay. So the input signal is first copied and fed to the 4 different layers. So whatever is the input signal that's coming from the input layer, each of this is one copy of that input goes to all of them, to basically it's copied to 4 different layers: 1, 2, 3, and 4. Okay, all convolution layers use the ReLU activation function. Note that the second set of convolution layer uses different kernel sizes, right? So you can see 1 by 1, 3 by 3, and 5 by 5. Okay, so allowing them to capture patterns at different scale. Also, please note that most of it has come by experimentation, and the intuition has basically built upon after the results. Okay, so you'll find a lot of terms that you'll wonder that how come this suddenly they figured out that, okay, since we needed to capture pattern at different scales, therefore we needed this kind of a pattern. No, the idea is that they experimented with various architectures, and then this intuition was built that this will help us capture patterns at different scales. Okay, so all right, so that intuition is at this, because since we have different sizes of kernel, right, 1 by 1, 3 by 3, 5 by 5, so the window that will move on the input records, the window that will move on input will be different sizes, and therefore at different scales we will be able to capture the capture the we'll be able to capture the patterns at different scale, right? So we are basically moving, having different sizes window on our input data. Okay, yes, we'll explain the depth concatenation. All right, so a question from Mintao is, are there 2 convolution layer in the GoogleNet? Yes. So this is an inception module. So this inception module will be used like multiple times. Okay, each inception module has 2 layers. Okay, this one has only 1 layer. Okay, and so on. A question from Ross is, as feature capture. That's correct. This allows them to capture the features in the towards the edge or anywhere, or different sizes of faces. That's what it will help. A question from James, can you explain what is depth concatenation doing? Good. So it is essentially concatenating the feature maps from all these layers into a single set of feature maps. All right. This parallel work is being combined into one singular results by depth concatenation. Great. Now, every single layer uses a stride of 1. Okay, you can see, and same padding, even the max pooling layer. So it outputs all the same height and width as is their inputs. Okay. So they are concatenated. They're not merged. They're just concatenated. All right. So otherwise, that would be called pooling if we were merging them. Okay. So basically, there was this singular module that was repeated again and again. The feature of this one is that it essentially using the 2 layers. Okay, one is with one here and another this. Second thing that it uses is the parallel network, as in the same signal is fed parallelly. Okay. This makes it possible to concatenate all the outputs along the depth dimension in the final concat layer, that is, stack the feature maps from all the top convolution layers. All right. So So it essentially stacks the feature maps from all the top convolution layer instead of merging in some way. Okay, so the question is that it's very strange that we are just processing one pixel at a time, correct? What does convolution one by one mean? And specifically with the stride of one, that means we are not missing anything. We're just going over one pixel at a time, right? Here also, we are just using one pixel at a time, one pixel at a time, one pixel at a time, and so on. Question is why? Why do we have convolution layers in the inception with one by one kernel? These layers cannot capture any features since they look at only one pixel at a time. These layers serve two purposes. One, they are configured to output many fewer feature maps than their inputs. So they serve as a bottleneck layer, meaning they reduce the dimensionality. This is particularly useful before 3 by 3 or 5 by 5 convolution since they are very computationally expensive layers. So the one by one layers, the one by one convolution layers, essentially um, drop many features, and they essentially work like bottleneck. Okay, while the same data is replicated parallelly, same input is replicated parallelly, so these all are trying to drop some of the features at once. Okay, so they are basically kind of bottleneck layer. They reduce the dimensionality, and when I say reduce dimensionality, essentially is that the filter is being applied across all the z directions, so we can control how many feature maps do we want in the output. So that's what the convolution is, right? That all the input feature layers, the input feature maps are basically called, so the filter is called against each of the layers in the input, and therefore those can be combined to form one. So the one by one layers are nothing but they are acting like a bottleneck layers. They combine and they essentially reduce the dimensionality, meaning then the feature maps in the inputs are being reduced or controlled by the convolution layer of one by one size. All right. So second, each pair of the convolution layer, like one by one, 3 by 3, and 1 by 1 and 5 by 5. Let me go back. 1 by 1, 3 by 3, 1 by 1, 5 by 5, and 1 by 1, 3 by 3, right? So each pair of convolution layer act like a single powerful convolution layer capable of capturing more patterns, more complex patterns. Indeed, instead of sweeping a linear classifier across the image, as a single convolution layer does, this pair of convolution layers sweeps a two-layer neural network across the image. All right. So instead of just using a single layer in case of convolution, here the same has been converted into two parts into a pair, and that pair is far more powerful than a single pass. Funnel equals bottleneck here. Yes, that's right. All right. Now, that was the inception part of the GoogleNet CNN. Now let's take a look at the actual one. So you can see that it uses many. Okay. So, okay, let me go back to answer a couple of questions. Question from Binta is, how can it sweeps a two-layer network across the image. Okay, so essentially um, it is essentially two layers being applied on single part of the image, single image, right? Let me just go back here. Yeah. So let's say we have an image. Let's say input image. The same image goes here, 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 and here. So instead of having a single convolution layer followed by max pool, you can think of it as a combination of two convolution layers. Now, question is that why does this help? This basically reduces dimensionality and makes this feeds lesser data to this one, lesser data such that it is faster. It is faster, and yes. Okay, so basically in this architecture, instead of going through one feature map at a time, so here we are applying two feature maps. Sorry, let me reiterate whatever I said. All right, so imagine that we are feeding some image to this Inception module. Okay, let's say we're feeding some image to this Inception module. The image, on that image, this filter will be applied, and this basically this whole translation, and this will generate one set of convolution layers. Then the same image will pass through this convolution first, followed by second convolution here, and then it'll generate some feature maps. Okay. Similarly, the same image will be fed to this convolution network, followed by this one, and then it'll generate some feature maps. And similarly here. And then all of those feature maps are concatenated or stacked on top of each other, on top of each other. And that's what is going on here. That's what is going on here. All right. So we are basically, these two layers are being, our image is passing through these two layers. All right. Okay. Now moving ahead. Was I able to answer your question, Binda? So here, so instead of applying one convolution network, one convolution on top of image, we are applying two. A question from Inta is, why can input skip the first layer and directly go to the second layer? It doesn't say that. It can't. The only thing is here, there is this one by one is basically it just taking the pixel as such and putting in the output. Just that the Z directions, if there are multiple feature maps in the input layer, those will be, on those we'll be able to apply the convolution. Okay. Okay, so it's not skipping the first layer and directly going to the second one. First one is being applied and then the second one is. Just that since it's a one by one, and so the only operation this particular only operation this convolution is doing is it is essentially translating each pixel alone into another set of pixels. That's all it is doing. Also, it is translating it is combining multiple layers, multiple feature maps into this output. Okay, that's what it is doing. Now, moving ahead. So question is why Inception modules have this one is done. Now let's take a look at the architecture of the GoogleNet CNN. Okay. So I hope I was able to answer Bintao. You can unmute and ask question if I was not able to answer. All right. All right. So let's move ahead. So GoogleNet has essentially many units of Inception module. Okay. So this is how the diagram looks like. It's a really deep neural network because first we have taken the inception out and explained elsewhere. And second, it's a single network we have broke into 3 columns and represented. Otherwise, you won't be able to represent on this page. So it includes 9 inception modules that contain 3 layers each. Okay, in this figure, inception modules are represented as boxes with a spinning top, and the 6 numbers in the inception modules represent the number of feature map outputs by each convolution layer in the module. Okay, so let me just show. Okay, so here, right? So there are total of how many numbers? 4 plus 2, 6, right? And okay, so these are essentially at this point. So these are the feature maps being outputted by each of the convolution layer inside the inception module. Okay, so in this figure, inception modules are represented with the boxes with spinning tops, and the 6 numbers in the inception module represent the number of feature maps output by each convolution layer in the module. All the convolution layers use ReLU activation function. Okay, all of the convolution layers are using ReLU, and let's go from the beginning. So there is an input image. On the input image, we are applying the first convolution. We are applying the first convolution, followed by max pool. So the first 2 layers divide the image's height and width by 4. So the area is divided by 16 to reduce the computational load. Okay. So since the image was 32, how much was it? 32 by 32, I think. And we are dividing it by 4 every time. So it becomes 64, right? 8 into 8. Right? So 32 by 32 became 8 into 8, that is 64. Okay. And right, that's what is happening here. And okay. All right. So the max pool is applied after the convolution. Okay. A question from Middaw is, could you post the new slides? It should be there in the same one. It's the same slide that we discussed last time also. Okay, I'll just give you. All right. All right. Great. Great. So So the first two layers divide the image's height and width by 4. Why? Because we have stride of 2. We're jumping by 2. Therefore, the height and width both are being divided by 4, and hence the area is divided by 16. Okay. This reduces the computational load. All right. Then the local response normalization layer ensures that the previous layer learns a wide variety of features. Right. So local response normalization, as we discussed, it essentially it is equivalent of dividing the value by summation of all the values. Okay. Summation of squares. Okay. Next is the two convolution layers follow where the first acts. Here we have first convolution layer, which is 1 by 1, which acts like a bottleneck, and it reduces and controls the dimensionality. And then we have second one with 3 by 3. So again, just like Inception, we can think of it like a single pair and single smart layer. Then again, local response normalization. So we have convolution followed by a pool, that's a standard one, then followed by normalization, then followed by two convolution networks, two convolution layers, and then again normalization, then followed by a pooling. Okay. Okay. So here we are using a max pool, and with a stride of 2. So okay. Afterwards, after the max pool, we come to the second column, right? The output of this max pool goes to this stack. Now, then comes the tall stack of 9 Inception modules, interleaved with a couple of max pooling layers to reduce the dimensionality and speed up the network. Next, we have an average pool layer that uses the kernel size of the feature maps with okay. So here in the average after the averaging pool, we are getting 192 feet. So after this one, we'll get after we concatenate this, there'll be just too many of layers. And afterwards, at this stage, we are using the average pool, which is generating 1024 total neuron. And afterwards, we are using a dropout strategy. Okay. So this average pool is essentially the global averaging pool. This is essentially the global averaging pool. Now, the last layers are self-explanatory. So you can see that the dropout is for regularization, then the fully connected layers with a softmax activation function to output estimated class probabilities. Okay. So this diagram is slightly simplified. The original GoogleNet architecture also included two auxiliary classifiers plugged on top of the third and sixth inceptions. Okay. So here 1, 2, 3 at this and somewhere here it had the auxiliary classifiers. Okay, they were both composed of one average pooling layer and one convolution layer, two fully connected layer, and a softmax activation function. So we had in this there were two extra modules called the auxiliary classifiers, and which basically had average pooling layer, convolution layer, and two fully connected layers. All right. Now, during the training, their loss was added to the overall loss. The goal was to fight the vanishing gradient descent problem and regularize the network. However, it was shown that their effect was relatively minor. Okay, so essentially it was basically here, it was a huge network of many layers. That's what that's what we learned from this diagram. So, all right, let me just go over it once more to give you a good idea. So first we have convolution and max pool, that's clear. Then local response normalization, and then again a pair of convolution, then local response normalization, and then max pool, followed by the inception. Okay, and then in the last we had averaging pool. Afterwards we had the regularization and the other parts. The dropout was for regularization, followed by fully connected 100 units, and then softmax. All right, so this is what was the Google Net. All right, now the next to this, the one that won 2015 ImageNet challenge was ResNet, called Residual Network or ResNet. It delivered an astounding top 5 error rate at around 3.6 using an extremely deep CNN composed of 152 layers. It was developed by Keming Hay and company. All right. So the key to be able to train such a deep neural network is to use skip connections, also called short circuit or shortcut connections. All right. So what is skip or shortcut connections? When a signal feeding into a layer is also added to the output of a layer located a bit higher up in the stack, then the skip or shortcut connection is formed. Let's take a look. So why skip shortcut connections are useful? So we have, let's say, okay, this is a bit of more like history class rather than a computing class. All right, so but the good news is that we are studying things that are very, 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 very recent. Okay, and now this is you see the being able to train 152 layers is actually possible because of many reasons. One, we have hardware. Second, we have the frameworks which could even utilize multiple computers. Second, third is that we have these algorithms which are performing great. So most of the training actually happens on the high-end GPUs. And I have not seen much of the training of deep neural network using the distributed computing. All right. Now, the ResNet basically skips some of the layers. Okay. Say for example, usually we have this kind of model, like we have input, layer 1, layer 2, and then output. These layer 1 and layer 2 can be summarized into HX, called the output of the hidden layers. Okay, so if you add the input X to the output of the network, that is, you add a skip connection. So here, instead of input going only through the layers, if we just add one more connection from here till the last, then the network will be forced to model fx equals hx minus x rather than simply hx. This is called residual learning. This is called residual learning. Okay. So the input is being input is skipping these layers to reach the output. So the overall hx, so this one is basically giving hx minus the input. Okay, that's the outcome of this one. So in this design, the most important differentiator was the skip connections. So why skip connections are useful? When you initialize a regular network, its weights are close to zero, correct? So the network just outputs very close values close to zero. Remember the vanishing gradient descent? If you add a skip connection, the resulting network just outputs a copy of its inputs. Okay. In other words, it initially models an identity function. So initially the values are very close to zero. Initially in any convolution network or any neural network. So if you skip a connection, the resultant is a copy of the actual one, and therefore the signal doesn't die. It is basically available at the next layer. Okay. In other words, it helps us model the identity function. All right. If the target function is very close to identity function, which is often the case, this will speed up the training considerably. Moreover, if you add many skip connections, the network can start making progress if several layers have not started learning yet. If if let's say there is a backpropagation and nothing is moving because the gradients have vanished, even then, since we are skipping the connections, even the next layers we could reach because our input could reach because of the skip connections. So so the signal can make way across the whole network, even if some of the layers are even dead or some of the layers have not started learning yet. So the deep residual network can be seen as a stack of residual units where each residual unit is a small neural network with a skip connection. All right. So this is our regular deep neural network where we have a sequential. Okay. So if there is the input this side, the layers that output close to zero, right? They are more. After a point of time, the signal dies down, and therefore we need the skip connections. All right. So imagine that we are having the input image here, and after like couple of layers, our signal has started to drop. So here, let's say after a couple of layers, the signal has died down. Because of skip connection, the signal would go to the next level. All right. So the architecture of ResNet, the ResNet starts exactly like GoogleNet, except without a dropout layer. In between, it's just a very deep stack of simple residual units. Each residual unit is composed of two convolution with batch normalization and ReLU, using 3 by 3 kernels and preserving the special dimensions, that is stride. Stride is 1 and same padding. Okay. So basically each residual unit has two convolution layer with batch normalization as well as ReLU as activation, using 3x3 kernels and preserving the spatial dimension, that is, we are having a stride of 1 and same padding. All right. So preserving the spatial dimension means that it is not jumping, it's not skipping the windows. Okay, that means the outputs dimensions are going to be same as the inputs dimensions. So we have input, then we have max pool, convolution, max pool, then there's a deep network, then average pool, fully connected, and then softmax. So average, fully connected, and softmax, except for the dropout, everything is same as GoogleNet, and a deep network of residual unit. So convolution, convolution, and then skip. CNN, convolution, convolution, and then skip, and so on. That's what this one contains. All right, that's what this one contains. So the ResNet is essentially a huge deep network of residual units. Note that number of feature maps is doubled every few residual units at the same time as the height and width is halved. So every time in the residual network unit, the width and height is halved. Okay, so uh, so number of feature maps are being doubling every few residual units, and at the same time their heights and widths are being reduced to half. That's what happens because of the stride 2. Okay, because of the stride 2. Okay, so since the height is changing now, if you think of it, the resultant of this convolution layer will have right now here after every two residual unit, we have a convolution layer that has a stride of 2. Okay, that has a stride of 2, because of which the height and width of this one will become half, and hence when we are concatenating this with the other one, what would happen is the dimensions would be different, and hence putting uh, concatenating different dimensions would be a problem. Okay, so since if you take a look at the convolution layer again here, when we pass our image or our data through this convolution layer, since this stride is 2, therefore some of the total number of pixels at this point will be half of the input. Okay, total number of width and height will be half. Therefore, the area of the layer that gets generated at this point will be half, while here there's no change in this, and hence at this point, the image that was there is left with 1/4 of the size, correct? And when we are skipping the layers and concatenating the input with the output, this one will have 4 times the size of the one which we left here, and hence there would be a problem. So how do we solve this problem? So on this side again, we put a simple convolution with 2 strides. Okay. So this is what was a modification to ResNet, and the each residual unit was essentially this. Each residual unit was like this. All right. Now, that was the winner of 2015. The winner of 2016 were Trim's Sosen team from China with an astounding error rate of 2.99% error. To achieve this, they trained combinations of previous models and joined them into an ensemble. Okay. All right. So what we learned as part of ensemble was that all we do is take a particular model and feed different set of data with different initial parameters or different type of parameters, and then we let all of those networks being trained and then start doing the prediction. And at the prediction time in ensemble, we just take the majority vote, either soft or hard. And that's what was done in 2016. So what they did was they used the Google Net and the ResNet in in an ensemble, and that gave them a really good performance. Okay, so ensemble is something that you can experiment with, even with any kind of model. All right, so they were able to bring down the error rate to 3%. That was that was the winner of 2016. Now the winner of 2017 were two. One was squeeze and excitation network. They're also based on Google Net, and they're also based on ResNet, both of them. You should take a look at these. And I also have to go through this one. All right, I have not yet gone through these two. All right, so let me just give you these URLs. Probably that will help you. Okay, so this was for the one winner, and this was another. Okay, so you must take a look at these models. These models are quite powerful, and basically, as we're speaking, there are a lot of research that is going on, and this is the area of the computing that is right now at the peak of the research. All right. So what did we conclude as part of CNN architectures? The field is moving rapidly with all sorts of architectures popping out every year. One clear trend is that CNNs keep getting deeper and deeper. They're also getting lighter, requiring fewer and fewer parameters. At present, the ResNet architecture is both the most powerful and arguably the simplest. So it is the one that you should probably use for now. Okay, and keep looking for the ImageNet challenge every year. So I think we need to update this after going through the 2017 winners. And yeah, so all right. Now, with respect to convolution, TensorFlow also offers a few other convolution layers. One is convolution 1D, right? This creates a convolution layer of one dimension input. This is useful, for example, in natural language processing, where a sentence may be represented by one dimension array of words, and the receptive field covers a few neighboring words. Okay. Then we have convolution 3D, CON 3D, creates a convolution layer of 3D inputs. See, conv2D underscore transpose creates a transpose convolution layer, sometimes called deconvolutional layer, which upsamples an image. Okay, so all right. So basically, we have multiple functions in the TensorFlow to create various kinds of convolution layer. And let's go through the notebooks once. All right. So essentially, what we did was we went through the history of most of the common networks. Let me just go through the Let me just go through the Jupyter Notebook. I'll open the terminal and pull my scripts. So this is a common proportion. Then we also have more functions like plot color image and plot image. Then we are importing TensorFlow. And here we have defined our own convolution layer. Okay. So we are just, okay. So first of all, we are just preparing the image. So here we are importing this function load sample image. Then we are loading the sample image, loading another sample image. Then we are picking a portion of this particular image into this. Then we are finding height, width, and channels. And then we are finding the mean with respect to the channels. That means we are finding the average of the colors at every xy. And that's what converts the image to mean to the grayscale. All right. And then okay. So here we are basically just reshaping it into the images layer. Okay, and this is how after the image, this is how it looks before before converting it to grayscale. This is how it would look. Okay, so plot image. Okay, let me just run it. So this is a colored version. This is the one after combining all the colors. This is how it looks. Okay, and this was the original image, out of which we have taken a small portion from somewhere, probably here, most likely, or here. Okay. Next is we are defining our filter. There are two filters. One is vertical strip and other is horizontal strip, just for showing you that what happens when we apply filters. Okay. Then we are creating a convolution layer. Here, we are feeding the feature maps. These are the So we just created a TensorFlow constant using the fmap. The fmap is something that we define the vertical and the horizontal strips. So we created a feature map, we created the convolution layer, and we just evaluated the convolution layer. So what it did was it just applied whatever we defined. It did not do any machine learning as such. Okay. All right. So after the here at this point, after we have computed the output, this should give us, yeah. Okay. Then we are trying to plot the output. This was the input, and this is how the output looks like. So you can see it's blurred. There are vertical lines. And when we are having the output with respect to the horizontal lines, so this is what it is. Okay. All right. Next is we are creating the here. We are creating the 2D and okay, same thing, whatever we did earlier. All right. So here we have created a data set out of the two images, China and flowers. And then we have created these filters, horizontal and vertical. Then we have basically created a placeholder. Afterwards, we are creating a convolution layer with the filters that we have defined above. And these are the strides. And for each of the set, for after we have prepared our graph, then is the time to create the session. And for the session, we are running this particular graph. Okay, so after running, uh, after running, this is the output that we're getting. All right. Okay, now let's take a look at how to do it using TensorFlow. That's okay. All right. Then we talked about valid and same padding. Okay. So what is that we are trying to do here? We are trying to create a filter called prime, and then we are defining the constant here with these values. Then we are defining the filters from the prime. Okay. Okay. So this is our valid convolution with the valid padding. This one is same padding. And so you can see here that the valid padding has less number of, okay. So what does it mean by, okay, okay. Okay, so after applying these values, this is what we get. After applying this filter, after applying this filter on X, this is what we get. Okay. Now, here's the pooling layer example. So pooling layer where we are filling it with zeros, then we are computing the values. Okay. So we're creating a max pool layer. So max pool is nothing, is very closer to the actual image. These two are very closer, just that this one is a little whitish because of the max pool, because we are just picking the maximum intensity pixels. So which one is lighter, this or this? Anybody? Second one, right? Yes. Why? Because this one is because of max pool. What we do in max pool is we pick a small window from here and we pick the best color out of it. A tiny window if you think of. So from this window, we are basically from this image, we're basically taking small pixels and taking the max of it. That's why this is more lighter and so on. So using this, you can see that we are able to visualize that we can modify the image to large extent. Okay. Then we talked about how to train the MNIST last time also, and we were able to run this. Yeah. All right. So in the meantime, I'll just explain to you what it means by the convolution layer. Okay. So let's start from here. So first of all, we are defining the inputs. This is our input X. This is Y, right? We have reshaped it. We have reshaped this one to fit to this. All right. Then we are defining Y, which is a placeholder. Then we are defining convolution layer 1 and 2. Okay. So the output of the first one goes to the second one. All right. Sorry, it got disconnected. All right. Are you able to see my screen? Was there any question that I did not answer before it got disrupted? James, Bentao, Pavan. So we were talking about the fully connected layer, then output, then the training part, the standard, the cross entropy followed by reduced loss and the optimizer, then training ops. Okay. And then finally, we are comparing the output. And finally, we save. All right. So that's what is going on here. And while we are running it, we're basically evaluating both. We are evaluating the training up as well as accuracy, just like usual. I'll have to run it. Let's see what goes here. All right, so that's pretty much, and we'll continue from reinforcement RNN, not reinforcement learning, recurrent neural network tomorrow. All right, we'll start our RNN tomorrow. Okay, so So we'll start the RNN discussion tomorrow and have a good day. All right. What are the final images of MNIST? Which one? Which final images? Okay, please. You mean the final outcome? All right, so the training is going on. All right. Okay. So here it's going to print the accuracy after every batch. That's what is the final outcome. Okay. If you increase the number of epochs to say 30 or 40, as well as if you increase the number of layers to more, you will get better results. All right. So here the outcome is approximately 97%, but you can actually just even if we copy the ResNet and just execute it, we should be able to achieve a very good performance around, it'll be 99.8. All right. So thank you, everyone. Have a good day. Bye-bye.